to today's lesson. Today we're going to look at the last of the identities for trigonometric functions. And we're going to start by looking at the sum and difference identities. And I'm going to just start by listing them, and then later on I'll show you some examples of how these are useful to us. The first one is, how do we expand the sine of the sum of two different angles? Now, be warned here, there is a temptation to want to think of expanding out brackets, and that is not the case here. This is the sine of two angles that happen to be added together. This is not expandable brackets. So in order to get rid of the brackets, we have to use the following identity. The sine of the first angle times the cosine of the second plus the cosine of the first times the sine of the second. You can see I'm going to have to write a little bit smaller to kind of cram all that in. Okay, so the next one I'm going to do is the sine of one angle minus another angle. And here's how that would expand. Sine of the first times the cosine of the second minus cosine of the first times the sine of the second. So that's sine of the sum of two angles and the sine of the difference of two angles, and how we expand these out. We also have formulas for the cosine of the sum of two angles, and that would look like this. Cosine of the first, cosine of the second minus. Now this is funny because you think, oh, it's sum, so this should be plus, but it isn't, it's minus. So watch out for that. Kind of a false friend, they call those. And minus sine of the first angle times sine of the second angle. And then we have, of course, the cosine of one angle minus another. And that would look like this. Pretty much the same. Cosine of the first times cosine of the second plus sine of the first times sine of the second. Okay. And then, of course, we have the formulas or identities for the sum of two angles when we look at a tangent. And this one's pretty different looking. It looks like this. Tangent of the first plus tangent of the second all over 1 minus tangent of the first angle times tangent of the second. So again, we have this is a plus, but here we have a minus. And the last of these sum difference identities that I'm listing is the tangent of one angle minus another angle. And how does that look? Well, very similar to this. Tangent of the first minus tangent of the second all over 1 plus tangent of the first times tangent of the second. Now, the important ones really aren't so much tangent. Those kind of rarely get used, but the sines and the cosines are very important. So I'm going to be doing some examples of that in a little while. But before I do that, I'm going to list the last batch of identities that we work with. And then you've got them all, and we'll show you some examples of these ones in action and how they're useful to us. So let's get rid of all these. By the way, in case you're starting to panic and think, I've got to memorize all these, you don't. Okay? They're provided for you on formula sheets, at least here in British Columbia, for your big provincial exam. So no person in their right mind would expect you to come in to an exam and have all these memorized. It's a matter of knowing how to work with them, and that's what's important. The following are called double angle identities, and you'll see why they're called double angle. Because we look at something like, well, what about sine of a double angle. Well, hence the name double angle identity. Sine of a double angle. Not just sine theta, but 2 times theta. What do we do with that? Well, it unravels and becomes 2 times sine theta times cos theta. Then we have cosine of a double angle. And this one's a little bit slipperier because it unravels 3 different ways. One of the ways it unravels is cos squared theta minus sine squared theta. Another way that it unravels is 2 times cos squared theta minus 1. And another way that it could unravel is 1 minus 2 times sine squared theta. So any one of these is a way to unravel cosine of a double angle. And I'll give you this one, although it's rarely used, and that is the tangent of a double angle. And that unravels as follows. 2 times tangent of theta, all divided by 1 minus tangent of theta squared. So there they are. Those are the identities. And I'm now going to show you what use these are to us. So we'll clear off the old board and start with our first one here. What we're going to try and do is get an exact value for the following. Sine of 11 pi over 12. And we want that to be exact. Oh. Okay. Otherwise, you could just put that into your calculator and find out a nice decimal approximation. So how do we do something like this if it has to be exact? Well, as soon as I think of the word exact here, I know I'm dealing with my special triangles. So I'm going to draw those just to refresh our memory. So I know I'm going to need one or both. And so this is the first of my special triangles. And I can see I'm working with radians here. So I'm going to put my angles here in radians. The angle in the corner here is pi by 3, or 60 degrees. And the angle up here is pi by 6, or 30 degrees. The other special triangle looks like this. We have root 2, 1, and 1. And each of these two angles is the same, pi by 4. So you've got to know your special triangles. They're really, really helpful. Okay, so how do I tackle this thing here? Well, let's see, what am I going to do? Well, I'm going to start by looking at this and its reference angle, because 11/12 is not any of my special angles here, and nor do I think I might be able to combine two angles through addition or subtraction and achieve 11/12. Certainly not with the angles that I'm working with. So I'm going to look at its reference angle. Now 11/12 is not quite all the way to 12/12 pi, so I'm going to kind of exaggerate. It would be this angle here, and the reference angle, now this is really the important one here, that is going to be 1/12 of pi. So that's the remaining 12th. The other 11/12, of course, are the angle itself. And according to the cast rule, sine is positive in that quadrant. So this sine of 11/12 pi is going to behave exactly the same as the sine of 1/12 pi. So the question could just as easily have said, find 1/12 pi, or pi over 12. Same thing. I don't even have to worry about changing it to negative, because it stays positive. This one I can achieve if I think of the difference of two of my special angles. If I think of it like this, instead of pi over 12, or 1/12, what if I took 4/12? Now 4/12 pi, we'll write that on the side here, 4/12 pi is exactly the same as 1/3 pi. And that would be this angle here, minus 3/12 pi. So if you think about this, okay, 4/12 minus 3/12 gives me my 1/12 pi. And what these angles are, this is pi over 3 minus pi over 4. Well, what I've done is I've taken this problem with an angle that I didn't have in any of my special triangles, and I've rewritten it using two angles that come from my special triangles. So now all I have to do is expand this using my trig identity. So how do we expand the sine of the difference of two angles? And I know I'm going to need the room here. So I'm going to start lower down here. But this is going to be the sine of the first one, cosine of the second one, minus cosine of the first one times the sine of the second. And all of these numbers I can get from my special triangle. Sine of pi by 3. Sine of pi by 3, well, that would be root 3 over 2. So that's what this guy is. Times cosine of pi by 4. Cosine of pi by 4 is 1 over root 2. Minus cosine of pi by 3. Well, here's pi by 3. Cosine is 1/2, 1 over 2. Times the sine of pi by 4, and the sine of pi by 4 is 1 over root 2. So there it is. Now I would combine that and make one fraction here. Since I'm running out of room, I'll just put it at the top here so we can see it. So what's my answer going to look like? Well, it's all going to be over 2 root 2, and I have root 3 minus 1. So there it is, and it's exact, which is kind of important. So the sine of 11/12 pi, that's what it is. So that's my first example. So that tells you why these identities are important. All right, let's see if we can work through something else equally as invigorating. The next example I thought we could work on is, let's see, cosine 225 degrees. And again, let's make that exact. All right, so let's start off with this. If I look at my reference angle, there's 180 degrees gets me to the other side of the lines here, on the other side of the x-axis. And then I'll swing down another 45 degrees to make 225. Well, there's my reference angle. So what I'm looking at is finding the cosine of 45 degrees. And according to the cast rule, only tangent should be positive in this quadrant, so this is going to have to be made negative. Now this one's kind of nice. I don't need a fancy identity. I don't need to add or subtract two angles. I can just work this one out directly from my special triangle. 45 degrees, and the cosine of that is 1 over root 2. So the answer here is negative 1 over root 2. So not too bad at all, that one was. A quick look at the picture where the angle was kind of unraveled it for us. All right, let's get on to some proofs now. It's nice to find exact values and all, but I think we need to see some proofs of trig identities in action. So we're going to try to prove this. 1 plus cosine of 2 theta all over sine 2 theta. We're going to attempt to prove that that equals cotangent of theta. All right. Now remember, you want to work each side independently, separately. So I look at this cotangent and I think to myself, well, I could certainly change this to cosine over sine. All right, so that's about as simple as I can make the right side. So I think I'm done there. What I need to do now is work on the left side a little bit. The one that I would change immediately is the one on the bottom. Cosine of a double angle. There is only one identity that works for that, and that is 2 times sine theta cos theta. By the way, how do I even know I should be unwrapping my double angles? Because over here I have no double angles. The fact that I have cosine of theta over sine of theta, okay, the single theta, kind of tells me I need to try to get out of the double angle business that's going on over here. So that's kind of the hint when you look at the right side. Now let's look at the top. We have 1 plus the cosine of a double angle. Now remember, we have 3 choices here. A smart choice would be one that might cancel with the one that we have out front. So which one do I want? Well, of the choices, I have cos squared minus sine squared. That wouldn't really get rid of the 1 for me. Then we have 2 cos squared minus 1. I think we're on to something if we did that. 2 cos squared theta minus 1. Now, by the way, if I did decide on a different version of cos 2 theta, say I didn't grab this one, it doesn't mean it's the end of the road for us. It just means there might be an extra step or two. So if you're wondering, well, I don't know if I would spot this particular choice here, it's not a big deal. It just means you might take a step extra. If I expand out the brackets here and think, well, 1 plus negative 1, that cancels. So what I have is 2 cos squared theta all over 2 sine theta cos theta. And I think you're going to see what happens here. The 2's cancel. And as you can probably guess, one of these cos thetas could cancel with the cos theta on the bottom. So let's get rid of that and one of those. And oh my goodness, cos theta over sine theta. Same thing. So left side equals the right side. Pretty neat. Now, we're off to what I'm going to do as my last example. So let's have a look at another proof with some other little tricks of the trade, and that'll be my last example. And I might just throw in where these things are undefined, because sometimes they talk about domain and what theta can't be and what it can be. What are they talking about there? Well, maybe that'll be made clear with this example. We're going to try to prove this. 1 plus sine theta, sine 2 theta. We're going to try to prove that that is in fact equal to sine theta plus cos theta all squared. Okay, that's what we're going to try to prove. Well, what could I do with this guy on the left side here? There really is only one way to swap out sine of 2 theta. So let's do that. We're going to get 1 plus 2 times sine theta times cos theta. Well, that's pretty much the end of the road for the left side. So really, the effort's going to be on the right side. Let's see what we can squeeze in over here. Well, remember, what does squared mean? It means I'm going to take this guy and times him by himself. So I'm going to get sine theta plus cos theta times the same thing. I'm just going to squish that in here. You may not be able to read this clearly, but it is simply saying sine theta plus cos theta times sine theta plus cos theta. So when I expand it out, I'm going to get sine squared theta. Then I'm going to get sine times cos and another sine times cos. So that means I got 2 of those guys. And then I've got lastly a plus cos squared theta. Now here's where a little grouping helps us. Sine squared plus cos squared can be replaced with, you got it, number 1, our favorite all-time identity. So this guy and this guy I'm taking out of the picture and I'm putting a 1 in its place. And oh my goodness, left side equals right side. Another proof down. Alright, sadly this one didn't have the disclaimers about domain that I was hoping for. So let me just explain what they're talking about. If in the course of a proof, at some point you have a fraction, and say in your fraction, okay, say at some point throughout the proof you've got something like a 1 over a sine theta, and blah blah blah, all kinds of other stuff. What we would say here is, well, you know that sine theta cannot equal 0, because otherwise we've got an undefined situation. And what does that mean in terms of theta? If sine theta isn't equal to 0, what does that mean about theta? It means that theta can't equal certain values. So let's just look at the graph of sine. And we know that when does sine equal 0? Well, at 0, at pi, 2 pi, and so on. So theta could not equal multiples of pi, where n is an element of the set of integers. That's what we're talking about. If at some point in our proof we've got a sine theta on the bottom, then we make the point about the domain here, or what theta can't be. Well, theta cannot equal multiples of pi. Otherwise, it's going to give us a 0 on the bottom. Okay? So that's what this sort of disclaimers about domain are when they creep into proofs. And you see them sometimes at the end of the proof and you go, well, what are they talking about? They're just talking about that you can't have an undefined fraction. Okay? And with that, we're kind of done with trig identities and trig proofs, and hope you liked it. We'll catch you later.